Okay, these would be the notes for finding square roots, comparing real numbers. There is a PDF with a note printout if you want to go ahead and do that first. Pause the video. First thing is, what is a square root? If b to the second power, b squared, is equal to a, that means b times b, then we say that b is a square root of a. So here's an example here. 3 to the second power equals 9, and, notice it's in parentheses, negative 3 squared equals 9 also. This has to be in parentheses because it's negative 3 times negative 3, which gives you a positive 9. If you have the negative on the outside, then the answer is just going to be negative. So 3 and negative 3 are both square roots of 9, so all square roots are going to end up having two answers. So here's an example here where we have the kind of the check mark here. That is called the radical symbol, and the number underneath there is called the radicand. And the bar just tells you what to take the square root of. So right now all we're doing is taking the square root of 9. We can have more than just one number in there. We can have an entire expression. So this would be equal to both positive and negative 3. So we can list both answers like this, but sometimes they'll just ask for one in particular, and we'll see that here in just a moment. Find the square root. This one has a negative sign out in front, so they're asking us for the negative square root of 9, so we would just write 3. Negative 3, sorry. This one just has the square root of 25, so this is called the principal root. It has no signs out front, so all we want is the positive value. So the square root of 25 would be 5, because 5 times 5 gives you 25. So 5 would be the square root. This one is asking for both, kind of like we did in the previous slide. The positive and negative square root of 64. That should be positive and negative 8. We sometimes refer to this as just plus or minus 8, because 8 times 8 is equal to 64, and negative 8 times negative 8 equals 64. Two answers. What this is. Let's get that out of there. Okay, perfect square. What is a perfect square? The square of an integer, that means raised to the second power, is called a perfect square. We can also call it a square root with an integer solution. So we take a square root, we end up with an integer. It's also referred to as a perfect square. Okay, so finding a perfect square is easy. All I got to do is take an integer and square it. So the number 6, if I square it, I get 36. This is a perfect square. 7 squared gives me 49. So 49 is a perfect square. That's how you find perfect squares. If I were to just take the square root of something, let's say the square root of 144, the solution of this is both positive and negative 12. So then I could say that 144 is also a perfect square because it has an integer solution. Okay, so we can square them, find perfect squares, or if I take the square root and I get an integer solution, it is also called a perfect square. The number underneath here called the radicand. Okay, so approximate square roots. Here you have to know your times tables, your perfect squares. The square root of 32, I'm going to go ahead and put this in the middle. And the next two closest perfect squares to that would be 25 and 36. And then I'm going to find the square root of each of these. Well, the square root of 25 is 5, and the square root of 36 is 6. So the square root of 32 is going to be somewhere between 5 and 6. But which one is it closer to? Well, we compare the numbers up here. 32, is it closer to 25 or is it closer to 36? It's actually closer to 36. So we're going to say that the square root of 32 is approximately 6. Now if you wanted to know more accurately than just 6, because it's 5 point something, you can just use a calculator with the square root, but same thing here. You just write approximately, so the square root of 103. Next two closest perfect squares would be 100 and 121. So take the square root of both of those, I get 10 and 11. And 103 is much closer to 100. So I'm going to approximate this to be about 10. Okay. Same thing here, only now we have a negative out in front. So I'm going to put the negative sign there, but when I'm doing my perfect square estimations, I'm going to ignore the negative sign because I don't really need that. It's just negative at the end. So the square root of 48, that would give me 49 on this side, 36 on this side. The square root of both of those would be 6 and 7. And this is really close to 49. So I'm going to call that approximately 7, but remember I have a negative, so I want the negative root, so negative 7. And if you put this in the calculator, that would be really close to 7, something like 6.89 or 99 or 95 or something like that. Irrational numbers. We've got rational numbers and we've got irrational numbers. Numbers that cannot be written in the form of a over b, where both a and b are integers, and b cannot be equal to 0, is called irrational. It cannot, let's underline this word, cannot be written in this form. Okay? If you put them in their decimal forms, they do not terminate or repeat. Okay? So anytime you take a square root of a non-perfect square, let's say I do 27, and again I got to put my approximation there. Let me use a calculator this time. 27 and the square root is approximately, and we're going to put 5.1961524, and my calculator stops at that number, but you'll see it does not actually stop, and there's no repeating pattern in this either. So then, since this does not terminate or repeat, we refer to this as being irrational. If it would terminate or repeat, or we can write it in this form where a and b are integer values, meaning no decimals or fractions in the numerator or denominator, then we would call it rational, but this one would have to be irrational. So non-perfect squares, like 27, when you take the square root, give you irrational. Another one you see quite often is pi. Again, not sure how they got there. Compare. Let's say we take two numbers like 4/3 and say the square root of 12. Yeah, let's do the square root of 12. If you want to compare using the greater than, less than symbols, we got to imagine where these would fit on a number line. So 4/3 is about 1.33, so I'm going to find where that is, right about here. We'll call that 4/3. And to know where the square root of 12 fits, you're going to have to go to the calculator and put that in. The square root of 12 is 3.46, so it's almost 3.5. So I'm going to find about the halfway point right here and call that the square root of 12. And keep in mind, anything further to the right on a number line is bigger. Bigger. I was going to write larger. It's bigger. And smaller would be to the left. So which of these numbers is actually bigger? The square root of 12. And we open up the inequality symbol towards the bigger number. And that's how you compare. So if you want to put things in order, of course you just imagine where they would fit on a number line left or right. And then you can go smallest to biggest or biggest to smallest, whichever order you're being asked for. Rational or irrational. I'll start with something like this. 9/2, rational or irrational. Well, first of all, these are integer values, so by definition it would be rational. So I'm going to put an R there. But if I were to divide that out, 9 divided by 2, I would get a -4.5, and you'll see that it is terminating. And that's part of the definition of rational. Let's do another one. 5/3. Well, first of all, these are both integer values, so by definition that is a rational, but put it into its decimal form, and you'll see you'll get 1.667. Eventually it rounds, but what happens here is you end up with a repeating decimal. Okay, so 1.6 repeating. So as long as it repeats, it would be rational. So rational numbers will terminate or repeat, or if they're written in this form where the numerator and denominator are both integer values. If you take the square root of a non-perfect square, the square root of 30 is about 5.47722. 5.47722255. It doesn't appear that it's going to create any pattern here, although it looks like there does be a repeating pattern, but this whole thing would have to repeat it again, and it doesn't appear to do that. So this one we would call irrational. Square root of 36, this has to be rational because the square root of 36 is 6, which is an integer that can be written as 6 over 1, which is a over b, where a and b are both integer values. And that's all we have on these.